Today we're going to be talking all about adiabatic dispersion. It's a unique method for humidification which offers some energy saving advantages, but also some important design considerations. With me again is my colleague David Baird. He's an application engineer here with DriSteem, and David has extensive field knowledge, which makes him the perfect guide for understanding when and how adiabatic solutions make sense. David, thanks again for joining me. Could you just give us maybe a quick refresher on what is adiabatic humidification and how does that differ from isothermal, which we talked about last time?
Well, adiabatic is the water droplets, and you're adding small little water droplets into the airstream and taking the energy out of the air in order to cause that phase change. And the result is you add moisture at the same time because the air is giving up energy to cause that phase change. It's resulting in a cooling effect. So adiabatic, think of it as water droplets, humidification, and cooling both at the same time.
Why would I consider using adiabatic versus an isothermal or steam-based system?
There's a couple of benefits. Adiabatic, because you don't have to put all the energy into the water initially, it's coming from the air instead. And so if you have excess heat in a process, as an example, I could use it for something practical and moisture addition. So that is something that might be beneficial. It's easy to pressurize water and send it around to multiple different spaces. Something to kind of think through is how much energy is the process consuming? Am I putting it into the water, causing the phase change? Am I taking it out of the air to cause the phase change? So that's one of the reasons why adiabatic. And if you want to do humidification and you want cooling, well, the only way to do it is adiabatic, because a steam system is going to add heat. It's not going to remove any of the energy. It's not going to cool the airstream.
And so when we're looking at different adiabatic solutions, what are ones that we should consider, especially if we're thinking about putting adiabatic humidification into an AHU? And what might be the best fit for that?
Well, there's a couple different ways. And we said it was water droplets. And it's a matter of how do we get the water droplets? You can pressurize the water really high and send it through a really small little nozzle, causing it to shatter into a lot of small particles. So a high pressure type system. You can drip water across a pad, wicking it away as the air moves across it. Different way of doing it, a way of media. You could do compressed air. Instead of pressurizing it really high, you could use a compressor that's under pressure along with the water and shatter it to small particle sizes. Otherwise, you can agitate water, vibrate water really rapidly and cause it to basically become a fine mist and an ultrasonic. All different ways, and what the particle size is changes, and what utilities you need in order to be able to do that.
Sure. So kind of when we're thinking about those utilities, like what are the design considerations that engineers should keep in mind when they're specifying a humidification system?
Well, anytime you're working with adiabatic, you think of it as a wet section. We're starting as little water droplets. So when you're designing within an air handler or ductwork, figure it's going to be wet. You're spraying water, whether really small particles or larger particles. So you have to plan for where can those materials handle being wet, and how do I get any droplets that don't get absorbed into the airstream, how do I get it out? You're thinking of a full-length drain pan, or multiple, depending upon how long it takes for that mist to dissipate. And then, okay, maybe you want to end the wet section, because you don't want to have forever in an air handler. Because an adiabatic type process, it doesn't happen as fast as steam. You're talking feet before that gets absorbed. And the more time that the water droplets have with the air, the more of it will be absorbed. You don't want to send it down the drain if you can avoid it.
Right.
And so having that time, okay, and then maybe you want to end it and having a mist eliminer at the end to make sure that you're not carrying any of that mist downstream onto your fans or other pieces of equipment. So you're kind of constraining what that is. And so you're planning for, okay, it's wet. So typically stainless steel, you got drain pans. The other thing is, if you're spraying water, you need clean water. You need reverse osmosis or DI water typically, because if you're shattering it through a small little nozzle, you don't want to cause mineral deposits to stay behind and cause it to clog up and not work. It's going to drive the pressure up. It's not going to spray mineral deposits around, you need to remove the mineral deposits ahead of time.
Yeah,
are important pieces.
And when you say DI water, that's deionized water, correct?
Yep. So typically, think of water, a reverse osmosis system, and then you add another process to kind of further polish it. You remove 95% of the mineral deposits typically in a reverse osmosis, and you take it a little bit further with deionized water.
Okay. So if we're thinking about putting an adiabatic system into an air handler, where in an air handler is the best place to put an adiabatic system?
Well, wherever you have space. Like I said, you need feet typically.
Right.
And so if we go back to the steam system, we said, where was the worst place to put it? Where the air was cooler. Well, the same principle applies. You want to have the heat because you're going to end up with a cooling effect. And so you need to have the heat initially. Whether it's already in the process or you're heating the air ahead of time, you're heating and then you're doing that humidification and cooling as well. If you want to use it for the cooling application, put it before your mechanical cooling system, like a chilled water coil or a DX coil as an example, because you can use that as the first stage of cooling. It may be more practical to do it with water to add the moisture in addition to get the cooling effect so you can run your compressors less. And just a more efficient, extending an economizer season as an example. When economizer, we're bringing outdoor air because it's nice, and maybe we can do it a little bit more because we're conditioning it by adding a little bit of moisture and cooling it before getting into the cooling system.
And so are there any additional provisions that we need to consider when we're putting these water droplets into the airstream?
As I said, you have to plan for it's wet. The whole section's wet, and so that's where, is the material's going to be able to handle being wet? As I said, typically stainless steel construction for it, and having ways to remove any water droplets that don't get absorbed are the key pieces that come into play. So plan for, it's a full-length drain pan for where that section is to remove it. And that's the biggest things you have to take into account that's different. And as I said, the space is longer than it would for a steam system. Steam, you don't have the water droplets, already vapor. Now you're causing that, starting with water droplets, and not all of it gets absorbed.
Okay. Is there any impact of the cooling effect from adiabatic humidification on HVAC controls?
It does. Like I said, if we're looking at using this, an adiabatic unit, as the first stage of cooling, then you have to let it run first, find out what you get out of it, then run your mechanical cooling system. And if you don't have the heat coming from the process, you have to know how much to warm it, because then you're going to have that cooling effect. So heating and cooling at the same time, but you're getting cooling and humidification at the same time. So you have to kind of balance what you want your target condition to be at the end. You're running additional heat if you need to. Take a Minnesota winter. If we wanted to do adiabatic humidification, we'd have to warm it up because it's not going to naturally come in warm.
Right.
If it's coming back from a process and it's already warm, then okay, we've got that. But that outdoor air coming in is cold. We need to have the heat in order to cause that phase change to happen. So determining what is the right set point to start with, and we have to maybe add a little bit of heat during winter, but shoulder seasons maybe not. And then staggering the mechanical cooling system after that. But then you don't want to run the adiabatic humidifier and run the relative humidity too high to cause mold and mildew potentially downstream. So there's a range at where it makes sense to do.
Sure. Well, David, I really appreciate that overview, helping us understand where adiabatic systems shine and how to design for them effectively. So, audience, thank you for your time today of joining us at this webcast. I invite you to join us for our next session, where we'll be diving a little bit more into steam generation methods, from boilers to standalone generators. You won't want to miss it. As always, if you want to learn more about any of the solutions that we've talked about in the last few videos, you can find a wealth of resources and knowledge right out on DriSteam.com. Thanks again for your time today. I'll see you next time.